holograms. They tell me that if you take just a little bit of a hologram and you look through it, you can still see the whole picture. The same is sort of true of analytic functions. All right, let's think about sine. So here I've got the graph of a function, y equals f of x, and in this case the function that I'm graphing is just sine. I want to think about this graph a little bit and just focus on this region right around the origin. Right? Imagine, if you will, that I've taken away all of the graph and I'm just looking at this little tiny piece right around the origin. What can I figure out about sine just by looking right around the origin? Well, if I look around the origin, I can figure out the value of sine at the origin. If I'm just looking around the origin, I can figure out the derivative of sine at the origin. I can figure out the second derivative of sine at the origin. I can figure out the third derivative of sine just by looking at this little tiny piece of the graph. I can figure out all of the derivatives of sine just by looking at this little tiny piece of the graph of sine. And if I can calculate all the derivatives of sine, that means that just by looking at that piece, I can write down the Taylor series for sine at 0. And we've already seen that the Taylor series for sine converges to sine everywhere. That's exactly right. We've seen that sine of x is equal to its Taylor series for all values of x. And what that means is that just this little tiny piece of sine just around the origin manages to encode the entire story about sine. All of the values of sine can be recovered just by knowing a little tiny piece of sine around the origin, because that's enough to calculate all the derivatives at 0, which is enough to recover the Taylor series, which recovers the entire function. Contrast that with something involving absolute value. Well, here's the graph of a function, so y equals f of x, but in this case the function is f of x equals the absolute value of x minus 1 minus 1. Now what happens if I zoom in on the origin? Well, this little piece of the graph just around the origin is enough to calculate some facts about f, right? What can I calculate just by looking right around the origin? Well, I can calculate that the value of this function is 0 when I plug in 0. I can calculate that the derivative of this function is negative 1 at 0. And I can calculate that all of the higher derivatives, all of the second, third, fourth, and so on derivatives at 0 are equal to 0. So yeah, this thing looks like a straight line around here, and that infinitesimal information at the point 0, just the derivatives at the point 0, are enough to recover the function around 0, on a whole interval around 0. Now, of course, I might have been tricked into thinking that the entire function just looked like this, right? I can't tell that there's this point where the function fails to be differentiable just when I'm looking over here. But nevertheless, just this infinitesimal information at a point is still enough to recover some information about the function in a whole interval around that point. Real analytic functions are really quite surprising. Infinitesimal information just at a point is giving you information on a whole interval. Sine, cosine, and e to the x are even better. In that case, the Taylor series converges to those functions everywhere, which means infinitesimal information at a single point on, say, the graph of sine, or at a single point on the graph of cosine, or at a single point on the graph of e to the x. That information is telling you everything about the entire function. Yeah, and entire is actually the word that's used. Entire describes functions like sine, where just the infinitesimal information at a point is enough to recover a power series with an infinite radius of convergence, converges everywhere to the entire function. So it's really like a hologram, right? Just a little tiny bit of a hologram records everything in the scene. And so too with, say, sine of x, right? Just a little tiny piece of sine reveals everything about the function.